So what happens if there's an implicitly defined function? What I mean by that is we can't separate the x, we can't separate the y. And so how are we going to take that derivative? And these usually make really cool graphs. Let's see what the graph of this one looks like. So we have x squared plus xy plus y cubed equals 0. And I'm not sure if Desmos is going to allow us. I don't think they are actually. Oh, there it is. And so that's what the graph looks like. This one's a little bit boring, but you can see if we zoom in right here, we get this kind of loop. So it's not actually a function. In order to know what the slope is here, we have to specify not just an x value, because at this x value, there's three different y values actually. So we have to specify an x and a y value, which when you see in these problems, when we do an implicit differentiation, they're specifying both coordinates, an x and a y, because it's going to require both of those. Because if I told you x was negative 0.1, which is right here, you wouldn't know which spot I'm talking about. There's 1, 2, 3 spots in the graph. You know, if I go down here, you'd see the third spot. So that's the downside to implicit differentiation. But we can't separate our y, so we can't just do an explicit differentiation like we were doing before. So what we have to pay attention to is what are we taking the derivative in respect to? In this case, we're taking the derivative in respect to x. Later on, when we do some other problems in related rates, we're going to take it in respect to time. So it's going to be a really similar set of procedures to this. So what's going to happen? So if we take this derivative, so let's just picture that squared. So we have x squared. So x is like the inner function, and squared, there we go, we got the outer function, then plus xy plus, and then once again we have an inner function of y and an outer function of cubed, and that equals 0. So I'm going to take the derivative in respect to every single thing here. So I'm going to take the derivative in respect to x squared, of x squared, and then I'm going to take the derivative, really it's dy dx. Well, we're finding dy dx. I'm just taking the derivative in respect to x of everything. And you'll kind of get this down where you don't have to do all this writing each time. So here's what's going to happen. We have like this inner outer function. So if we use the chain rule on this, I'm going to bring down the 2. So we'll have 2 times x to the 1. You can kind of picture this inner function. And then times the derivative of the inside is dx dx. So dx dx, that just cancels out, goes away. So that's why we don't, anytime we take the derivative of x squared in respect to x, we've always been doing it in respect to x, when we take the derivative of x squared, it just becomes 2x. This dx dx just goes away. You'll see why I'm doing this. Let's come back to this product rule, because that's a product, so we got to do that later on. But right here, derivative in respect to y cubed, this might make a little more sense now. So I'm going to bring the y down, and it becomes squared, and then we have this inner function of x. We don't know what y is. It could just be f of x equals 2x squared minus 3. It could be any function, right? So we're going to take the derivative of that, derivative of y in respect to x. So we get dy dx. And that doesn't cancel out. That stays. And guess what? That's what we're looking for. So we're going to get this by itself in the end. Derivative of 0 is 0. Here's the hard part, product rule. So we have to do the whole f prime times g plus f times g prime. So derivative of x is just 1 times y, so we'll just get plus y. And then x times the derivative of y is dy dx. All right, derivative of y is just dy dx. That's what we saw earlier, derivative of y. When we took the derivative of the inside, it just became dy dx. Let's give a little more space for this. All right, so we saw the product rule that happened right here. Here's everything. I'm going to clean it up a bit. Let's just call the dy dx y prime. Makes things look a little bit nicer. So we have 2x plus y. And you'll end up just shortcutting this to the y prime in the end after you get the hang of the idea. Plus 3y squared times y prime equals 0. It's a little bit easier to look at it that way. Now the goal is we want to get dy dx, so we want to get this by itself. So everything without a y prime, I'm going to move over to the right side. And I'll have xy prime plus 3y squared y prime equals negative 2x minus y. And then once again, our goal to get y prime by itself, I'm going to factor that out. Since they both have y prime in common, I'll factor it out to the front, and we'll be left with x plus 3y squared. And then we'll just go ahead and divide this over to the other side. And y prime, which is dy dx, what we're looking for, equals negative 2x minus y over x plus 3y squared. It's important to realize that that negative is only applying to 2. Now we could factor it out. So this is the answer. This is good. Sometimes, multiple choice, they might factor that negative out to the front, and this becomes a positive 2x plus y. We're just factoring out of both terms from the top. That way we can put it in the front. So they might change that a bit. So kind of a lengthy process. I mean, we broke it down to a little more of the details, right? So let's go ahead. Let's take a look at this example. And I'll leave these for you guys to do, but I'll write the solutions. So we'll go through this one a little faster now that we saw the details. All right, so we're going to take the derivative of everything in respect to x. Right, because it's dy dx. So I'm going to have 2x minus 3, and then I'm going to do the product rule on the x and the y. Make sure you use those parentheses because you're going to have to distribute the negative 3 applies to the product there. So derivative of f is 1, derivative of x is 1 times y plus x times y prime. Plus 2y times y prime. And remember, you can see the above example on how, 2 times y and then the derivative of y is just y prime. We have to do the chain rule. And derivative of 1 is 0. That's actually probably one of the biggest mistakes is some people forget to take the derivative of that constant on the other side. All right, let's distribute that negative 3. Move everything over. I'm going to add the 3y and then subtract the 2x. Quite an easy process once you get the hang of it. At first, a little bit confusing. I think this is where they lost me in high school calculus. I was like, what is going on? Then factor out the y prime. And I'm going to put the negative to the right and the positive in front. You could rearrange those. Oops, 2y. Divide it to the other side. And then we want this derivative at the point 1, 0. So that means your x is 1. And this is just showing you the dy dx at 1, 0. Just another notation for that when we're using that dy dx notation. So I get negative 2 over negative 3, which is 2/3. I hope that's correct. Kind of rushing there because class is going to start right now. So that's it. Like I said, I'll have the solutions up for these. They should already be up whenever you're watching this video.